Right, so as we continue, we're going to look at the quotient rule for differentiation. So what I have here is a quotient, a fraction. Now don't think that every time you see a fraction bar that means you have to do the quotient rule. You can certainly do an algebraic rewrite on it and just use the simple power rule. So we need to kind of observe the fraction before we jump in and do the quotient rule. But if you decide you need to do the quotient rule, this is what it's going to look like. All right, let's bring in the derivative operator. All right, if I find the derivative of a quotient, I'm going to go right to the answer on the right-hand side here. I'm building the answer. All right, and in the answer, the denominator of the answer is going to be the denominator of the problem squared. Notice just copy over the denominator of the problem, put a quantity square on it, and you're good to go. Now, how you build the numerator for the derivative of a quotient? You build the numerator by starting with the denominator of the problem, no derivative, but you multiply it by the derivative of the numerator. In a quotient situation, we don't add, but we subtract. Remember how in the product rule we added? Well, in the quotient rule we have to subtract. All right, and then to subtract, it's just the reverse of this. So denominator times the derivative of the numerator minus the numerator left alone times g prime. There it is, finally. Finding a derivative of the denominator. All right, so it's just an algorithm. It's a set of steps. Let's see if we can use the quotient rule correctly. So here's our example. Something about my word at work slows everything down. So hopefully, again, not too much pain for you. Okay, let's look at this quotient. Classic example of, here's a problem where you have to use the quotient rule. Not really much of an option. I mean, I could get pretty complicated, but right here I'm going, okay, I'm going to use the quotient rule. Some of you might be looking at the idea of bringing up the denominator and wrapping it in parentheses and bringing it up as a -1. Well, then you're going to have to use the product rule. So I don't think that's any easier. I think I'd jump right to the quotient rule. All right, so let's begin to build the answer for the derivative. Okay, applying the formula, it's the denominator of the problem, quantity squared. Easy enough. Always start there. Then you can start and kick off the numerator with the denominator not squared, but the denominator of the problem, x squared plus 1, times the derivative of the numerator. And I know some of you are thinking, gosh, I know the derivative of the numerator is 5. Well, go ahead and write that down. You don't have to do the whole setup. Minus the numerator left alone times the derivative of the denominator. For the structure, we're writing everything down. Oh, goodness. All right. Never would we want to FOIL out the denominator because ultimately we want to try and simplify, reduce. Okay, so if we have it in factored form, it's easily identifiable to determine if it can reduce or not, or simplify. All right, so we still have more work to do in the numerator. So here, that derivative is 5. So where am I going to put 5? I'm going to put it up front. I'll come back and distribute the 5 through later. Minus, come over here, before you write down 5x minus 2, kind of take a look at this derivative. It's 2x. I'll put that right up front. Okay, what's left to do? A little cleanup on the numerator, and we're good to go. Cleaning up the numerator, collecting like terms, it looks like I'm going to have negative 5x squared plus 4x plus 5. Even if I factored the numerator or could factor the numerator, I wouldn't get one of these binomials, so I couldn't simplify any further. So I'm done. That's the quotient rule, pretty much in a nutshell. So let's look at a couple more examples. All right, so we see a quotient. There's that. I mean, definitely that's a visual. We see a fraction bar. It's a quotient. Do we have to use the quotient rule? No. So we want to really make sure and take the time to study the problem before we just jump right into the quotient rule, because there might be an easier technique, and there is. Think of the constant multiplier rule along with the power rule. So y prime equals, I'm just going to kind of think about this being all by itself as a constant multiplier, finding the derivative of this variable. So I'm going to multiply 4 times 5. I'm going to get 20. Keep x. Drop the exponent down by 1 to 3. And don't forget about the 8 that's down here. You could do a little simplifying, dividing out a common factor of 4 from the numbers. So I'll have 5x cubed divided by 2. So I didn't have to do the quotient rule, even though there was a quotient. All right, is the quotient rule necessary on example 3? Nope. You could rewrite it using algebra. Notice I'm not going to the prime. Make sure don't put prime on here. This is 9/5 x to the negative 2. Let's apply the power rule. Negative 2 times 9, negative 18. Oh no, don't mess up. Ah, that's a negative. Negative 18. Okay. And then it's going to be over 5. Keep the x, drop the exponent down by 1 to negative 3. Okay, you can clean this up. You can rewrite it. You can drop the negative exponent to the denominator. So just because you see a fraction doesn't mean that you have to apply the quotient rule. Okay, let's continue. I know I've only done one problem with the quotient rule, but not too bad to apply it. Okay, let me come back up here now and just to save some space, and I'm going to put problem 4 right next to problem 1. All right. Goodness, how long was this problem? I guess we'll be putting it next to it, so I think I'll stop right here. Well, as you can see, I decided to put 4 beside 2. All right. Do we have to use the quotient rule? Nope. You can slide this whole numerator off, do a rewrite on it. You could pull out the 1/6 and put it in front as a constant multiplier. If you're dividing by a constant, this might be a good strategy when you're trying to find the derivative. Slide off the numerator, multiply by the coefficient 1/6. Let's go to the prime. Let's apply the constant multiplier rule. We've got 1/6 out front. Now dig in and look inside here. Let's find the derivative of each term, 2x plus 3. If you want to go back and restack this with 6 in the denominator, fine. Okay. If you want to distribute the 1/6, then create 2 different terms and reduce each term, fine. Otherwise, I'm going to leave my answer just like this. I think we need to apply the quotient rule again. All right, on number 5, I don't really see anything that would allow me to rewrite that and avoid the quotient rule. I think I'm pretty much committed to the quotient rule. So let's go right to the prime. Easiest thing to do is to build your answer, your derivative answer, by starting with the denominator and quantity squaring it, and then immediately you can begin the numerator with the denominator not squared. Denominator times the derivative of 7x minus the numerator left alone times the derivative of the denominator. Ooh. All right, go back to the numerator, take care of this derivative. It's 7. We know we're going to put it up front. I'll have to come back in the next step and distribute the 7 through. Minus always on the quotient rule, plus on the product rule. This derivative is 2. Multiply it by 7x, and we're going to get 14x. A little bit of cleanup in the numerator, and we should be good to go. (14x minus 21) minus another 14x. Oh, that's convenient. I'm kind of running out of a page here, so I'm going to go over to the side. Otherwise, I prefer to go down. So those will cancel. I'm left with negative 21 over quantity 2x minus 3 squared. All right. The quotient rule is very helpful too in finding the derivatives of the other 4 trig functions. So far our knowledge about the derivatives of trig functions is limited to 2 functions. Okay? You might remember the derivative of sine is cosine, and the derivative of cosine is negative sine. So what about the other 4 trig functions? Okay, well, they all have derivatives as well. Okay, and so the quotient rule allows us to find those derivatives. So I'm going to prove maybe 1, maybe 2 of the trig derivatives for the other 4 trig functions. Okay, and then unfortunately I wish I had better news. We're just going to have to memorize them all. All right, so that says derivatives of the other trig functions. Derivatives of the other trig. Well, I'm supposed to say that. I don't know what happened to the D and the E. Oh my goodness. All right, now that we've learned about the quotient rule, we're going to find the derivative of tangent, and here's why. In order for us to find the derivative of tangent, we could rewrite it as sine over cosine, sine x over cosine x. Now, once we see the derivation of the derivative formula for tangent, you never have to derive it again. You just have to memorize it. So just kind of be aware of that. But I want you to see where the derivative of tangent comes from, so we're going to derive it at least once. All right, tangent is sine over cosine. Oh, I have a quotient. Let me use the quotient rule. Y prime equals the denominator squared. Okay, usually when we write it down with the power, we put the square on the trig function like that. So the denominator times the derivative of sine, which is cosine. I'm going to avoid writing it all out to save time. Minus the numerator, sine x, times the derivative of the denominator, which is negative sine x. So I'm going to take the negative, and I'm going to come all the way up front here, and I'm going to make an adjustment to a plus, but I have to record the sine x for that derivative. Clean up the numerator. In print, we usually put the square here, or you could do parentheses on the outside with the square. Can I cancel these 2 cosines? No, because I have to be able to cancel it from everything. Remember, if it doesn't divide out of everything on top, then you can't divide it with bottom. What do you remember about cosine squared plus sine squared, or better yet, sine squared plus cosine squared? Hopefully from pre-cal, you remember that cosine squared plus sine squared is equal to 1. We're pretty much finished. We were pretty much finished right here with this line, but what is common practice in calculus with the derivative of tangent? Well, they don't like to have fractions in your answers for the derivatives, so that's why we're doing all this extra pre-cal work. 1 over cosine is secant. So if I have 1 over cosine is secant and I have 1 over cosine again, that's another secant, this is really going to change to secant squared x. That's a reciprocal property from pre-cal. So done. The derivative of tangent is secant squared. So I'm going to start to build kind of a pattern over here for us. Well, actually, you know, I'll just wait. I'm going to do another derivation and then I'll put it all together for us, looking at all 4 trig derivatives. So I'm not going to find the derivative of cotangent. I'm going to find the derivative of secant, and then we're going to look at some patterns. So what's the derivative of secant? Well, we're going to first change it to 1 over cosine, using pre-cal to help us. We're going to notice we have a quotient. We're going to use the quotient rule for differentiation. Start the numerator of the answer with the denominator, so cosine x times the derivative of 1, well, that's going to be 0, minus the numerator 1 times the derivative of the denominator, which is negative sign. So we'll write sign down, but the negative will come back up here and we'll adjust this way. Right. This whole product goes to 0. We're left with sine x over cosine squared x. Okay. As I mentioned earlier, we don't like to have fractions in our derivative answers. Okay, so we're going to have to do some pre-cal. Okay, so let's split this up. Meaning I'm going to expand cosine squared x in the denominator, putting cosine x under each of these 2 fractions I'm multiplying. This is 1, and this is sine x here. Okay, using pre-cal again. In our reciprocal properties, we know y prime is equal to, this will change to secant x times tangent x. Like I said, you don't have to derive these formulas again. All you have to do is memorize the derivative formulas for each of the 6 trig functions, which that's enough in itself, okay? All right, so I derived 2 derivatives. There are 2 more, but I'm not going to take the time to do that. We're just going to look at patterns, okay? So let's get a little more space to do that. Okay, what you see right here are the 2 derivatives that we've previously found. Okay, so let's look at those answers. See if we can make some assumptions. Okay. All right, here we go. All right, so the derivative of sine is cosine, but the derivative of cosine will go to negative sine of x. Okay, notice now that right before you, I put down the derivative of tangent and the derivative of cotangent. I didn't derive the derivative of cotangent, but I did derive the derivative of tangent. Okay, and we saw that to be, come on, secant squared x. Okay, so thinking about what we have here and what we have here, the derivative of the cotangent should be negative. Okay, and this is actually going to be negative cosecant squared x if we were to derive it. All right, so let me write down the next ones. Okay, so add these 2 to our list. Come on, little red pen. We derived the derivative of secant to be secant x tangent x. So what's the derivative of its cofunction, or the derivative of cosecant? Well, that's going to be negative cosecant x.
Good afternoon, Mitchell High School. It is now 3:30.
Times cotangent x.
Declare the building, students.
Okay, well, if you haven't cleared the building, you need to. We have 6 trig functions here, all of which we now witness or see. We see their derivatives. Okay, so I wish I had better news that you have to memorize it. All right, I think Mr. McCandless is done. So let's do hopefully some quick examples because I think I'm running out of time here. Okay, all right. So let's see how these derivatives kind of play out. Okay, we're going to try and do some examples here. So come on, switch over, pen. Okay, y equals x minus equals x minus tangent x. All right, so as I scan this, it looks like the sum and difference rule. Okay, the derivative of just x is 1 minus the derivative of tangent is secant squared. I'm sure there's something from pre-cal we can do with that, but we're going to leave it just like that. Okay, what about y equals x times secant x? Okay, as we look through this, it's not the sum and difference rule. It's one big group. It's one big term that has different factors in it. And I'm not going to switch colors of my pen. That slows me down. Okay, this is going to be the product rule with the new trig derivatives. So we've got an f and a g. Go to y prime. So it's the first times the derivative of the second plus the second factor left alone, secant x, times the derivative of the first factor. All right, so let's focus our attention on secant x's derivative. Well, that's going to be secant x times tangent x. So you might as well leave the x in front and just record the derivative secant x tangent x. Over here, the derivative of x is 1, and so we would just write down plus secant x. The only other thing you might see is that since secant x is a common factor, they might have brought it up front and factored it out. Otherwise, you don't have to do that. It's simplified. You're just deciding to change to a different form by pulling out the secant x. Okay. We'll have more work to do with these trig derivatives, but I wanted to at least look at a couple of basic examples with that. So thanks for hanging in there.